Hello and welcome to part 8 of this video playlist about the preparation of pyridines. This video is about the preparation and transformations of pyridine N oxides. These compounds are easy to prepare from pyridines and allow a number of chemical transformations that cannot be performed with the parent pyridines. Typical oxidants suitable for the preparation of pyridine N oxides include hydrogen peroxide, peracids, dioxyranes, and oxygen in combination with some catalyst. Reduction of pyridine N oxides to pyridines is often done with phosphorus trichloride or other phosphorus 3 derivatives because of the simplicity, selectivity, mild reaction conditions, and high yields attainable. Catalytic hydrogenation or reductions with zinc have, however, also been reported and may be more environmentally friendly and less expensive. Unlike pyridines, N oxides tend to react with electrophiles at positions 2 and 4. Electrophilic halogenations and nitrations at these positions have been reported, for instance. Carbon-centered radicals will also add to these positions if possible. In the presence of strong acids, however, protonation at oxygen occurs, and the N oxides then show a similar reactivity as simple pyridines or pyridinium salts. Sulfonations, for example, occur at position 3. Hard electrophiles, such as acyl halides, protons, or sulfonyl chlorides, react mainly at oxygen. The resulting products can sometimes be isolated and react like pyridinium salts. Organopalladium and Grignard reagents tend to add to position 2 of pyridine N oxides. Polar organometallics may, however, also bring about deprotonation of the N oxide, mostly at position 2. One characteristic transformation of pyridine N oxides is derivatization at oxygen followed by addition of a nucleophile at positions 2 or 4 and elimination, as sketched here. A broad selection of nucleophiles can be introduced using this strategy, including halides, cyanide, and amines. Unfortunately, the regioselectivity of this reaction may vary, depending on the precise conditions and reagents chosen. Occasionally, the nucleophile adds at position 3 by the mechanism shown here, but 2 and 4 substituted pyridines are the most common products. If pyridine N oxides with alkyl groups at positions 2 or 4 are subjected to these reaction conditions, the nucleophile will usually add to these alkyl groups, as sketched here. I'll show you specific examples of such reactions in a minute. But first some examples of the preparation of pyridine N oxides. Here, a 2-vinylpyridine was oxidized with hydrogen peroxide in acetic acid. A good yield of the N oxide resulted, without any oxidation of the furane or the olefin. One point worth mentioning is that low molecular weight pyridine N oxides are polar, sometimes even hygroscopic compounds, and a standard aqueous workup may not always be possible. In such instances, reagents should be chosen carefully to facilitate the workup. Peracids such as MCPBA have also been used to oxidize pyridines. In this example, epoxidation of the alkene was slower than oxidation at nitrogen, and again the N oxide was obtained in good yield. Even examples of the enantioselective oxidation of pyridines have been reported. Here, such an oxidation was performed with hydrogen peroxide and a carbodiamide in the presence of 10% of a peptide ester. The enantioselectivity wasn't very high, though. Let's check some specific examples of the deoxygenation of pyridine N oxides. Catalytic hydrogenation is usually the least expensive and most environmentally friendly strategy, but other functional groups may be hydrogenated too, as in this example. Here, along with the pyridine N oxide, also a nitroalkane was reduced to the amine. Highly chemoselective deoxygenations can be achieved with phosphorus trichloride. Here, for instance, a complete reduction required only 15 minutes at room temperature, and no reduction of or addition to the electron-deficient alkene occurred. A further practical reagent is zinc in the presence of ammonium salts. In this example, the reduction was again very fast and the formyl group remained unchanged. This is another example of such a zinc-mediated deoxygenation. The target product was obtained almost quantitatively. Reaction of pyridine N oxides with acetic anhydride is a convenient procedure for the preparation of 2-acetoxy or 2-hydroxypyridines. Here, for instance, only one isomer was formed in high yield. The reaction was achieved by refluxing the pyridine N oxide in a huge excess of acetic anhydride, but such a large excess is not necessary. Regioselectivities are not always as high as in the previous example. When 2-picoline N oxide was heated with 2 equivalents of acetic anhydride, a mixture of 3 products resulted. The main product was the expected 2-acetoxymethylpyridine, but substantial amounts of 3-acetoxypicolines were also obtained. As already mentioned, these 3-acetoxy isomers are formed when acetate adds to the intermediate dihydropyridine, as sketched here. Also, the reaction of 4-picoline N oxide with acetic anhydride can yield various products. In this example, the authors isolated after hydrolysis a low yield of 4-hydroxymethylpyridine. Under slightly different conditions, however, again after hydrolysis a 3-hydroxypicoline could be obtained. Thus, results of these reactions can be difficult to predict correctly. Apart from these mishaps, however, many examples of high-yielding reactions with acetic anhydride have been reported. Here, the expected product was obtained in excellent yield by heating with only 3 equivalents of acetic anhydride in toluene. I'll show you now some examples of the halogenation of pyridine N oxides. A high preference for halogenation at positions 2 or 4 can be achieved by avoiding strongly acidic reaction conditions. In this example of chlorination, after 50% conversion, sodium hydroxide was added to prevent acidification. Chlorination occurred mainly at position 4. When pyridines or their N oxides have electron-donating substituents, these usually dominate the regioselectivity of electrophilic substitutions. This was the case in this example of bromination. The acids were required to enhance the reactivity of NBS. Here an N oxide was brominated by treatment with lithium terzbutoxide and carbon tetrabromide. This reaction probably proceeded by intermediate deprotonation of the starting material. Unlike pyridines, pyridine N oxides can be nitrated selectively and in high yield at position 4, as shown here. The authors also found that after acylation at oxygen, nitration at position 3 was possible with silver nitrate, but the yield was low. More common than electrophilic substitutions at pyridine N oxides without deoxygenation is the addition of nucleophiles to the ring with simultaneous cleavage of the nitrogen-oxygen bond. Many examples of the deoxychlorination of pyridine N oxides with phosphorus oxychloride have been reported. Unfortunately, the regioselectivity is sometimes low, as in this example. With 3-picoline N oxide, a useless mixture of isomers was obtained. This poor regioselectivity could be improved, however, by addition of an excess of tetramethylpiperidine and by conducting the reaction with phosphorus oxychloride at 5 degrees Celsius. Under these conditions, mainly 1 chloropicoline resulted. Most deoxychlorinations of pyridine N oxides with phosphorus oxychloride yield 2 or 4 chloropyridines. This here is a rare example where the chlorination occurred at position 3. The mechanism was probably similar to that of the formation of 3-acetoxypyridines discussed earlier. This is another rare example of deoxychlorination at position 3. Instead of phosphorus oxychloride, thionyl chloride was used, and the reaction already proceeded at 60 degrees Celsius. One strategy to introduce other nucleophiles than halides at position 2 of pyridines is shown here. Methylation of pyridine N oxides at oxygen isn't easy, but can be achieved by heating with neat dimethyl sulfate. Treatment of the resulting salt with an aqueous solution of sodium cyanide mainly yielded a 2-cyanopyridine. The same transformation can be achieved in one step with trimethylsilyl cyanide. In this example, a huge excess of this reagent was required and the yield was low, but this may have been due to the unprotected amino group of the starting N-oxide. Let's have a look at some carbon-carbon bond-forming reactions. Alkyl halides only rarely undergo palladium-catalyzed substitutions because alkyl-palladium complexes readily fragment into alkenes and a palladium hydride. With an excess of 2-picoline N-oxide, however, cyclohexyl bromide could be cleanly arylated, as shown here. This is an example of the addition of a carbon-centered radical to pyridine N-oxide. The radical was generated by hydrogen abstraction from MTBE with terz-butyl hydroperoxide. Deprotonated sulfonyl hydrazones can also be used as carbon nucleophiles to alkylate N-oxides, as in this example. Here, pyridine N-oxide was allylated with allyl acetate and palladium acetate, but isomerization yielded a mixture of two vinylated N-oxides. Potassium fluoride was used as base. Like deoxyhalogenations or cyanations, pyridine N-oxides alkylated or acylated at oxygen can also yield 2-alkyl or 2-aryl pyridines upon reaction with carbon nucleophiles. In this example, the N-oxide was activated by benzoylation and then treated with a slight excess of an enamine. The yield of alkyl pyridine wasn't high, but the reagents were inexpensive and the reaction easy to perform. Treatment of pyridine N-oxides with Grignard reagents can cause ring cleavage and yield oximes, as shown here. These can, however, be cyclized again to pyridines by heating with acetic anhydride. As discussed earlier, occasionally nucleophiles add to position 3 of activated pyridine N-oxides. In this example, a high yield of a 3-alkylated picoline resulted upon heating the N-oxide with an electron-deficient alkyne. This reaction probably proceeded by formation of the intermediates shown here, followed by hydrolysis and decarboxylation. The reaction of alkynes with pyridine N-oxides can also yield pyridines alkylated at position 3 by an intramolecular Cope-type rearrangement. Acid and gold catalysis were required in this example to bring about the formation of an enol ether by addition of the N-oxide to the alkyne. Pyridine N-oxides can also be deprotonated by strong bases and then alkylated with carbon electrophiles. In this example, isopropyl magnesium chloride was used as base and cyclohexanone as electrophile, and the reaction sequence was conducted at -78°C. Although pyridine N-oxides are more electron-rich than their parent pyridines, acylation occurs first at oxygen and not at carbon. Acyl radicals in some transition metal acyl complexes, however, can acylate N-oxides at carbon. Here, a benzoyl palladium complex was formed by oxidation of benzyl alcohol with potassium persulfate. Addition to the N-oxide of 2-chloropyridine yielded mainly the acylated N-oxide. Few reports of the electrophilic amination of pyridine N-oxides have been published. In this example, amination with an isoxazole yielded a substituted 2-aminopyridine N-oxide. Many more examples of deoxyaminations are known, though. Here, an N-oxide was activated with tosyl chloride in the presence of saccharin. A good yield of N-pyridyl saccharin resulted, which could be hydrolyzed with dilute sulfuric acid to the corresponding aminopyridine. Similarly, pyridine N-oxides can also be converted into 2-aminopyridines by treatment with trifluoroacetic anhydride and pyridine, followed by hydrasinolysis of the intermediate pyridinium salt. Both reactions gave high yields. Treatment of pyridine N-oxides with cyanamides and methane sulfonic acid yielded 2-pyridyl ureas. Interestingly, with 2-methoxypyridine, a mixture of two isomers resulted, probably again by the mechanism discussed earlier. By the way, ureas are not convenient precursors to amines, because these can be extremely resistant to hydrolysis. On this and the next 2 slides there are some newer articles about the chemistry of pyridine N oxides, which you can also find in the description of this video. That's it. I hope you found this and the other videos of this playlist useful. And thanks to those of you who subscribed to my channel, which is meant to be a reference work on organic synthesis. I'll keep uploading new playlists every 2 or 3 months.